Hi everybody, Dr. Burns here. We're going to take a look today at section 7.3, which gets more into some different properties of this Laplace transform, and we can kind of see how these fit together. At first, this may seem a little bit daunting, so just kind of hang in there with me, take the notes with me, go through the examples with me, and as we work through, like I said, as we keep going through the chapter, we'll see where these properties come into play and how we're going to use them later to solve some differential equations. So I want to start with the translation property. The translation property says that if we have a Laplace transform for a given function, then the Laplace transform of e to the a t, so if we take that function and we multiply it by e to the a t, that can be found by just doing the Laplace transform, capital F, of s minus a. So it's like a translation. And like I said, we'll see some examples, so just hang tight. I know this is a little fuzzy at first, but you'll get it. And you'll see where we use this for. The second property is the Laplace transform of the derivative. And it says as long as we have a continuous function, little f of t, and we know that its derivative is piecewise continuous, meaning at least continuous on the intervals if it's a piecewise function. Don't worry about that. Here's the gist of it. The Laplace transform of f prime is going to be equal to s times the Laplace transform of f, the original function. Let me use a bracket here instead. There we go. Minus f of 0. And this is really a special case, this Laplace transform of the derivative. This is really a special case of this next rule, the Laplace transform of higher order derivatives. This is basically an extension of what we just talked about. The Laplace transform of the nth derivative, so any derivative, any higher order derivative of a function is going to be s to the n of the Laplace transform of f minus s to the n minus 1 times f of 0 minus s to the n minus 2, and it kind of follows a pattern here. N minus 2 times f prime of 0, and then minus dot dot dot, all the way down to the n minus 1th derivative evaluated at 0. And so how is this property above it a special case of this property? Well, if I'm talking about the first derivative, that means that, for this example, that means that this n that they're working with would just be 1, right? So that means I have s to the first power times the Laplace transform of f minus f of 0. F of 0 is essentially what that is. This is the original function. Think about that. F of the n minus 1th derivative. Well, if you're talking about the nth derivative, go up one level. That's the original function. So that's just f of 0. And again, I know this is a little bit confusing. Hang in there. We'll summarize all of this later in the chapter, and you'll kind of see where these properties are particularly useful. But what I wanted to just point out was that this is just a special case of this. And then finally, we want to look at the Laplace transform of t to the n, so like a polynomial function, t to the n times f of t, then that would be negative 1 to the n times the nth derivative of that Laplace transform with respect to s. And this basically what that does is it gives us another option or another method for computing a Laplace transform based on a given transform that we already have. So let's look at how we would use these to solve some different problems. Take a look at example 1. We want to find the Laplace transform of t times the sine of bt, where b is a constant. So the idea is this is giving us some flexibility in terms of how to calculate these Laplace transforms without having to go through that definition from the previous section where we use the the improper integral. So let's look at what we've got here. We know from the previous section, I gave you a chart with some common Laplace transforms on it. Let me go back to that. I think it was in the class examples from 7.2. Here it is, and this chart is a nice chart. You'll get to use this on the test, so don't worry about that, but you got to recognize them when you see them. Sine of bt, for example, the Laplace transform for that is b over s squared plus b squared. So we can start with that. So let's go back down here. If I want let's start with that. We've got f, we know that the Laplace transform of sine of bt is equal to b over s squared plus b squared. So what this essentially is an application of this last property right here where n equals 1 because they want t times that sine of bt function. So if I want to find that Laplace transform, I'm going to go ahead according to this property right here. I need to find the first derivative. So I need df ds, which would be the derivative of this Laplace transform right here with respect to s. S is the variable, b is the constant. This would require, you could either do a quotient, don't do a quotient rule. Let's do a chain rule, and I'm going to write this as b times s squared plus b squared to the negative first. So I can apply a chain rule. Remember, b is a constant. So your derivative here becomes, bring the negative 1 to the front, you get negative b, derivative of the outer, right, with a negative 2, evaluated at the inner, times derivative of the inner, which is 2s. So that gives me negative 2bs over, I'm going to get rid of that negative exponent, s squared plus b squared squared. So what this property says is the Laplace transform now of t times sine of bt is going to be equal to negative 1 to the nth power, n is 1 of course, so negative 1 to the first power times the first derivative, which I just computed. So that was negative 2bs over s squared plus b squared to the second power. And of course, just clean that up a little bit. We get 2bs over s squared plus b squared to the second power. And that's going to be our Laplace transform for t sine of bt. All right, number 2 says use known transforms and properties to show that the Laplace transform of e to the at times sine of bt is equal to this expression. Well, from the previous example, we said that the Laplace transform of just sine of bt, I should say it's from the previous example, but again, this is from that chart from the last lesson. A known transform for that is equal to b over s squared plus b squared. So this translation property we have up here says that if I want to find the Laplace transform of e to the at times some other function, I'm just going to take that Laplace transform and substitute s minus a in place of the s. So let's write that out. So I'm using that translation property. So the Laplace transform of e to the at times sine of bt is going to be b over s minus a squared plus b squared. And if we, of course, simplify that, we get this expression right here. A squared minus 2as plus s squared plus b squared. And that's it right there. And I want to point out one other thing, by the way, from that chart. We're going to go back to this chart all the time in this chapter, but right here, notice these two little properties right here, e to the at sine of bt and e to the at cosine of bt. Notice what they're using here. Oh, and actually this one as well, come to think of it. This is that translation property that we're talking about. That's it right there. So these are common. They will come up a lot as we go through this chapter. But I wanted you to see in this section how that translation property applies, and that's where those rules came from. Let's do one more. It says use the known transformations and properties to find the Laplace transform of cosine bt. Now I do realize that's in that chart that I just showed you, but I want to show you how these properties could be used to help us figure it out if we needed it. All right, suppose that we start with f of t is the function sine of bt. And we know that, of course, by now, maybe we have it memorized. We've used it a few times in these examples. Sine of bt, the Laplace transform for that is b over s squared plus b squared. Well, the derivative of sine of bt is using a chain rule, right? bt is the inner function, would be b times the cosine of bt. So the Laplace transform of the derivative of sine of bt, so the derivative I'm using the derivative property, where is it? Right here, this one, the Laplace transform of the derivative, so the Laplace of f prime is equal to s, and by the way, that looks like a prime. I think that was a 1 when I was trying to remind you that it was a 1, so let me erase that real quick. Here it is again. So it's s times the Laplace transform of f minus f of 0. So let's go back and let's write that out. So that property says the Laplace transform of f prime is s times the Laplace transform of f of s minus f of 0. So that means that the Laplace transform of b cosine of bt is going to be equal to s times the Laplace transform of f, which was what we started with. That's the b over s squared plus b squared minus f of 0, but f of 0 would be sine of 0, right? Sine of 0, and that, of course, would just be 0, so we don't have to worry about that. And so the Laplace transform, then, of b cosine of bt is equal to s times b over s squared plus b squared. And b is a constant, so one property of Laplace transforms when you have a constant multiple is you can move them to the front. So that means that b times the Laplace transform of cosine of bt is equal to sb over s squared plus b squared. So remember, what I was looking for was the Laplace transform of cosine of bt. So to get rid of that b, since it's a constant, I can just divide it to the other side. So then I have Laplace transform of cosine of bt. When you divide by b, this b will cross out, and I'm left with s over s squared plus b squared. And that is the Laplace transform for the cosine of bt. And by the way, that is, if you go back, that is in our table. Let me go back to 7.2. I'm going to keep going back to this table because we're going to use this all throughout the chapter. Here it is right there. The Laplace transform of cosine of bt using that derivative property is s over s squared plus b squared. And you can see that we just verified that using the derivative property. So in class, what we'll do tomorrow is just practice working with these properties and just kind of getting comfortable with them to find some of these transforms. So make sure you bring your notes, and I'll see you then.